So good afternoon. My name is Nick Tranter. I'm the Business Development Manager for New Energy at Stryde. And this presentation today will be about how we can unlock land seismic in geothermal. And for this, I'll be using an example of an urban seismic survey which was acquired last year for geothermal exploration, and also trying to demonstrate how land seismic acquisition is becoming more cost effective and sustainable, whilst also delivering high resolution seismic data. So the outline of this presentation is as follows. Firstly, we'll see why seismic is useful in geothermal and also open up on its historic perception. We'll look at the recent evolution of land seismic technology, and then we'll move on to this sustainable seismic project example, where we'll look at the objectives of the project and also look at the technologies used on it. And then finally, we'll conclude with the results on this project, both from an operational perspective and also look at the seismic data which was produced and comparing that to some legacy data in the region. And then finally, we'll finish off with just some conclusions on a high level. So why is seismic required in geothermal? And I think first of all, we need to remember that seismic as a technology is something which has been used by the oil and gas sector for many decades. It is the proven method of choice in exploring the subsurface, and this can be used to target prospects or plays anywhere in the depths from several hundred meters down to thousands of meters. Now, to maximize the potential of any geothermal system, whether it be open loop, closed loop, hydrothermal system or EGS, the subsurface needs to be understood. So firstly, seismic, this can be used to actually find the geothermal system itself. And what we see is that most geothermal targets do lie within the range of seismic imaging resolution. Then following this initial exploration and looking into drilling, we need to monitor these geothermal sites, especially during, for example, during the injection phase. And this is where we can use 4D seismic to take snapshots of the subsurface over time to look at where the injection or where the fluids may be moving in the subsurface. We also have natural and induced seismicity, so this is a relatively hot topic these days. So this is where the operator needs to prove that the injection is not creating unwanted mini earthquakes. So really using seismic receiver equipment to listen passively to the natural and induced seismicity plays quite a key role in delivering data to analyze this. And then finally, we need to look at drilling activity. And prior to this, identifying any shallow hazards such as faults, casts, or gas pockets, as it's important for these to be imaged to prevent serious incidents during drilling. But if we look at why seismic is not often used as much as it should be in geothermal, we need to look at some of the reasons for this. And principally, the main reason for this is cost. Seismic acquisition with conventional technologies is expensive, especially if high density surveys are required. And this is why it's really only been exclusive to the oil and gas industry over many decades. And if we look at the geothermal sector, we see that legacy data is commonly used. And when it comes to new acquisition, it's usually only 2D data or sparse 3D, which is really affordable for both the geothermal and renewable industries. There's also the perceived complexity of seismic acquisition, and you have to source both the equipment and labour in quite large volumes. Permitting can take months, if not years. And there's also the large HSSE risk, which can be relatively overwhelming to manage when you're looking at the numbers involved. Experienced resources are also required. You have to manage who have to manage the acquisition. We also have to look at experienced teams to process the data. And then also the actual seismic itself needs to be interpreted. And if you package all of this together, it does really start having an impact on feasibility and even the perceived value of seismic to the end user. And I think the good news is that seismic technology has evolved a lot in recent years. It is now significantly a lot more compact, lighter, more environmentally friendly, simpler to use, and importantly, a lot lower cost. I think one of the best examples of this is if we look for the onshore seismic receiver market. So the image on the left-hand side, this is a selection of that's probably the most common commercially available geophones and accelerometers. And it really does show the drive towards miniaturization of this technology, also whilst trying to maintain the data quality which is output from it. And what this miniaturization enables is that higher density surveys can be acquired, providing better data, but they can also be acquired quicker and safer when compared to conventional surveys, and this is all at lower cost. And similar to seismic receivers, seismic sources have also followed this similar path. At the center image here, this is a portable active seismic source, which is being developed by the University of Tokyo. It's a relatively advanced research project, but it really shows that a seismic source has now shrunk to a size of something which can fit in a rucksack. Some examples of commercially available source options. We have the pinpoint source. So this is a portable impulse source that can be operated by a crew on foot with no need to clear lines. And on the far right hand image, we have a mini eVibe. So this is a powerful device, but it's also designed to minimize access clearance, and it can fit into a standard container to really ease transportation. And to try and demonstrate this recent evolution of land seismic, I wanted to share with you a case study. So this is based on a geothermal project between Stryde and Seismic Mechatronics, in which a high resolution 2D seismic survey was acquired through the middle of a Dutch urban city centre. Now, the objectives for this project were to acquire this 7.5 kilometre 2D line, which was to support a district heating programme, with the seismic data being used to determine the heat layer in the subsurface, but also to build up this knowledge of the subsurface ahead of drilling. We also wanted to demonstrate that low cost, sustainable and low environmental impact surveys can be acquired in urban settings through the technology used. And finally, we wanted to test various seismic acquisition equipment and compare the results and data from this equipment with an existing conventional survey which had been acquired in the area. So two main seismic equipment technologies were used in this survey. The source was the Storm 10 eVibe. So this is a technology which was initially developed out of Delft University of Technology and is now commercialized through Seismic Mechatronics. The eVibe, it's an interesting piece of kit. It's an electric seismic source, and it's based on a direct drive electromagnetic motor. So this uses permanent magnetics and coil windings to generate frictionless movements. And what this really enables is that it delivers a strong and powerful source in a relatively compact box. And I think moreover, when used of an electric vehicle, zero carbon acquisition can be made possible, really eliminating any CO2 emissions from this source activity. And for this particular survey, along this 7.5 kilometre profile, the source spacing was at 10 metres. Some scouting was performed before the project, but for accuracy, all source points were measured through an RTK GPS receiver installed on the eVibe itself. And similar to most seismic projects, testing was performed ahead of the acquisition, and it was decided to go through an upsweep range of 2 to 100 hertz, and this was at 24-second sweeps. And this all enabled the imaging of the target reservoir on the subsurface. And then just looking at the receiver system, which was used in the project. So this was the Stryde technology used to record the data. Now the Stryde node, which you can see here in the centre of the image, is the smallest and lightest autonomous node in the market. And what we're seeing is that these nodes are progressively replacing cable system, which really frees up the acquisition contractor away from the bulkiness and access limitations which historic systems may have provided. And these newer autonomous nodes are really enabling urban seismic surveys become more achievable. And for this particular project, 1,500 of these Stryde nodes were deployed along this 7.5 kilometre line, and this is at a 5 metre spacing. And the Stryde nodes were programmed to record at 1 millisecond sample rate for 10 hours per day during the night time when the data was being recorded. And with each of these Stryde nodes, they're very lightweight, about 150 grams and about 13 centimeters in height. And this enables them to be easily concealed and buried even in urban environments, meaning that theft, which is quite a common issue was minimised. And by burying them as well, this also helps in reducing noise effect on the data. Now, just to look at some of the results from the project and starting off with the operational efficiencies and sustainability. So for the source effort, so the seismic profile, it did run through the city centre. So a lot of noise was expected from traffic and also railroad, which ran close to the survey itself. Therefore, to improve the personal safety and also minimise this external noise, it was decided that acquisition would take place at night during midnight and 5 a.m. And during the course of the project, the average daily productivity for this was about 200 sweeps achieved per night. And with the eVibe source itself, this only consisted of a crew of 2 people. There was one observer travelling in an electric ATV just ahead of the eVibe, and there was just one person operating the eVibe itself. Now for the receivers themselves, so this is the Stryde nodes. So all 1,500 nodes were deployed by 3 people in just 2 days. And for the retrieval, all the nodes were required in 1 day, were retrieved in 1 day by just 2 people. This deployment and retrieval was done on foot as per the image in the bottom right, and there was just 1 compact electric vehicle used to support the deployment and retrieval operations. And this is relatively critical and improve the safety. What we see is that road-related accidents are often the highest risk for seismic surveys. So really reducing the amount of vehicles on a project is quite a critical aspect for us. And overall, for an urban survey, this was a quick project. The survey was completed in 1 week, and no HSSE incidents were reported, and all the instruments retrieved showed 100% reliability. And I think finally, no permits were required for this survey, principally due to the technology used, but also due to the survey accommodating a lot of the local stakeholders. Now, in terms of seismic imaging, so the data was processed using a pre-stat time migration. As previously mentioned, with an inner city location, a lot of the shot records were contaminated with environmental noise, so we had to have various adaptive noise attenuation techniques to remove this, which was successful. And then following the processing itself, the data was compared with a 2D data set which was acquired in 2021. This was a conventional 2D data set using a high effort explosive source. And this legacy 2021 data set does intersect perpendicular to the eVibe and the Stryde 2D line, as per the base map you can see here in the center of the slide. And when we compare the 2 data sets, what we see is that the conventional 2021 acquired data, when you compare it to the newly acquired 2022 eVibe data and eVibe and Stryde data, is we can see that the data is high quality. So this is in panels B compared to the older data in panels A. We see that the data has better continuity, sharper imaging, both in the near surface and also the deeper subsurface. So moving on to conclusions and what next. So looking at the project itself, so a low environmental impact seismic survey was successfully acquired through an urban setting in the Netherlands, which was used for geothermal exploration. And for this project, recently developed technologies were successfully deployed and used. As a source, this was the Seismic Mechatronics Stormer 10 eVibe, and for the receivers, this was the Stryde node for sensing and recording the data itself. Now, the survey was acquired in a cost-effective manner, and we estimate that this was at about half the cost of a conventional survey. And we're also able to minimise land disruption during the project itself and had a reduced environmental footprint. And this was through using smaller field crews and having a quick operational time frame, and also the use of electric vehicles. I think importantly, the actual data quality itself was not compromised, which enabled the subsurface to be further de-risked ahead of the next phases of this geothermal project. And from a lessons learned perspective on future projects, we'll actually probably try and space the nodes out in a wider spacing at 10 meters rather than 5 meters, and look to maintain the data itself. So what do we see next for land seismic and geothermal? So I think this case study goes some way to demonstrating that zero carbon seismic acquisition can be achieved. This is something we're working towards, and for this particular case study we've looked at in this presentation, generators were used for powering the eVibe source, but moving forwards these will be replaced by battery options. We can also see that moving forwards, novel ways of acquiring seismic data, such as passive surveys or producing pseudo 3Ds from conventional 2D surveys. These both bring lower costs and becoming options which are looked at more and more. And then finally, with the use of new technologies, these will allow surveys to be acquired in environments and conditions which were previously just deemed unfeasible. So to end on and look at sort of the key takeaway message, with this trial, several promising technologies have been used which really do demonstrate that land seismic is more accessible than ever before for geothermal exploration. And this has really enabled a detailed understanding of the subsurface, which helps de-risk the project. And I think as a sector, both in geothermal and across renewables, if we are to achieve the similar success rates which we see in the hydrocarbon industry, then utilising this geothermal data, especially seismic, is going to be essential for us. And with land seismic itself, it is adapting relatively quickly. It's becoming a lot more sustainable, safer, and with low environmental impact, and enabling better working relationships with the stakeholders on the ground. And then to finish, I'd just like to say thank you to some of the contributors to this presentation today, from Seismic Mechatronics, Delft University of Technology, Dayaborough Geophysical, and my colleagues at Stryde. So thank you very much for listening.